Again, this is our winter Skywarn training for the 2023-2024 winter. So first off, which office ends up covering you? The Skywarn talk is certainly available to people who live anywhere in the Carolinas. It's going to be focusing on the 31 counties in central North Carolina that the Raleigh office covers. North Carolina is covered by portions of 7 different offices. There are offices in Raleigh, Wilmington, and Morehead City. Those are the 3 offices located in North Carolina. Northeastern North Carolina is covered by the office in Wakefield, Virginia. That's between Richmond and Norfolk. The northwestern portion of the state is covered by the Blacksburg, Virginia office. Much of western North Carolina is covered by the Greenville, Spartanburg, South Carolina office. And we have 2 counties in the far west, Cherokee and Clay, that are covered by the Knoxville, Tri-Cities, Tennessee office. So why do we have a winter Skywarn presentation? The mission of the National Weather Service is to protect life and property, and winter storms are certainly a threat to both of those things. In many locations in our region, winter impacts are relatively rare, and winter impacts are generally broader, while the summer impacts can be more localized. So when we do end up having some sort of winter impact, it'll affect a lot more people in all likelihood. So this is a general outline for what we'll be going over in the presentation. Winter hazards, climatology of snow, some of our products and those definitions, a few miscellaneous objects, and then finally what we're hoping that you can report to us. So starting off, winter hazards. What are some primary winter hazards that we have here in central North Carolina? Heavy snow, even if it doesn't occur all that often. Ice can certainly end up being a big one, and then also cold outbreaks. So the image on the left-hand side is from an ice storm that we had several years ago, and you can tell that that tree is not supposed to be leaning like that. Just so much ice coated on the branches are just causing that tree to sag. If you end up looking at that image on the right-hand side, that is from Glenwood Avenue back in February of 2014. For those who are familiar with the Research Triangle Park area, Raleigh-Durham, this is on US 70 Glenwood Avenue facing east, just to the east of 540. The Angus Barn is probably about 100 yards behind this photo, and that's heading up the hill as you're looking back towards Raleigh. And I mean, it looks like something out of a disaster film. Sometimes we end up handling our winter a little bit better than others here in North Carolina. So some snowfall statistics for Raleigh. These records go back to 1887. A normal seasonal snowfall is 5.2 inches, and that is over the last 30 years, 1991 to 2020. We do climatology figures every 10 years, and they cover a 30-year period. The largest seasonal snowfall that we had was 31.6 inches all the way back in the 1892-1893 winter. The largest monthly snowfall that we've had was 25.8 inches in January of 2000. The largest snowstorm was 20.3 inches. That occurred over the 24th and 25th of 2000. And the largest single day snowfall was 17.9 inches on, I believe that was a Tuesday, January 25th. So we had another 2.4 inches on the 24th. And the highest snow depth, no surprise, was 20 inches of snow on January 26th. Taking a look for snowfall statistics at one of our other climate sites, Greensboro. We have 3 primary climate sites, Raleigh, Greensboro, and Fayetteville. However, we do not have a snow observer in Fayetteville for these at this official climate site. The Greensboro records began in 1903. The normal seasonal snowfall is 7.1 inches, again, from 1991 to 2020. The largest seasonal snowfall in Greensboro was 32.5 inches of snow back in 1926 and 1927. The heaviest month of snow that's ever occurred was 22.9 inches in January of 1966. The largest snowstorm was not the same one as Raleigh. It was 20 inches and it occurred on March 3rd, 1927. And that was also the largest one-day snowfall. And I forgot to say this earlier when I was beginning the presentation. I will end up taking questions at the end of the presentation. All right, so let's talk about different types of precipitation. Snow and rain we're all a bit more familiar with, but what's the difference between sleet and freezing rain? Both of these types of precipitation require alternating layers of cold and warm air. So you can see the animated graphic here. Freezing rain, the precipitation typically starts as snow, and it will melt in that warmer layer, the red area, but the layer of cold air at the surface is too shallow to allow that raindrop to freeze mid-air. So the rain doesn't actually freeze until it reaches the surface. The difference with sleet is that you still have a thick enough warm layer to completely melt your snowflake into a liquid drop. But that layer of cold air at the surface is thick enough that it will allow the raindrop to completely refreeze in the air, and that's why it ends up landing as a pellet. We'll spend a couple more slides going over sleet and freezing rain. Again, snow is when you have the cold layer, the entire atmosphere is below freezing, or you might have a very shallow layer at the surface that's above freezing, but it's not enough to melt the snowflake. Again, sleet, you're going to have a shallow warm layer if our x-axis is looking at the temperature. And so there's a shallow warm layer that is deep enough to melt the snowflake, but the cold layer is thick enough that the raindrop can completely refreeze before it hits the ground and falls as sleet. While freezing rain has the deep warm layer melting a snowflake into a raindrop, but it doesn't have a chance to refreeze before it hits the ground, so it freezes on contact. This is a great graphic that I just saw last week. I had never seen anything like this before, and I immediately knew that I wanted to put it in the presentation. It was courtesy of the Maryland Office of Preparedness and Response. Again, describing the difference between sleet and freezing rain. The sleet are those pellets, the sprinkles that you end up having on the frosting. Meanwhile, freezing rain is when you have a glaze of ice on the surface. So that's another way to visualize the difference between sleet and freezing rain. So again, freezing rain, just spending a little bit more time on this. What is it? It's liquid precipitation that freezes on contact with a cold surface as it enters a shallow layer of temperatures at or below 32 degrees. So we talked about some snow, we talked about some ice. Let's talk about some of the cold weather that we end up having. The coldest low temperature on record in Raleigh was -9 degrees Fahrenheit. That occurred on January 21st, 1985. The second coldest day by comparison was -3. So the fact that our coldest day here was colder by 6 degrees than the next coldest day just tells you how extreme that is. By comparison, we've had 105 degrees recorded in Raleigh 3 times, and I don't know how many more times we've had 104. So the fact that that 9 degrees below is 6 degrees colder, it's just a ridiculously cold temperature for here. And the high temperature that day was 17 degrees. The coldest high temperature that we had was all the way back in 1899 when the high only made it to 10 degrees. There wasn't that much of a temperature swing that day. The low temperature that day was 4 degrees. If we look at Greensboro, also January 21st, 1985, they dropped to -8 degrees. The high temperature in Greensboro that day was 21 degrees. The coldest high temperature has occurred 3 times, I guess I have a typo there. 1917, 1966, and 1899. The low temperature those days was 4 and 3 degrees. And finally, Fayetteville, its coldest low temperature was only -1, also on January 21st and January 22nd, 1985. The high temperature those days, 49 and 21. The coldest high temperature was recorded back in 1917, where the high was 18 degrees and the low temperature that day was 2 degrees. Taking a look at some recent warm spells that we've had in Raleigh during the colder season, I would end up showing you cold spells that we've had, but we haven't had cold months recently compared to all-time levels. So back in 2020, we were tied for the 3rd warmest November with a mean temperature averaging all of the highs and all of the lows to 55.8 degrees. I won't read all of these numbers out to you, but I will tell you the general format that I went with on the slide. So the November normal from 1991 to 2020 was 51.5 degrees. The record warmest November was 58.3 degrees. That's occurred twice in 1931 and 1985. And the lowest mean average temperature for November was 42.5 degrees, and that occurred in 1976. I will end up noting that the warmest temperature that we've ever had in a day in February occurred earlier this year. It was 85 degrees in Raleigh on February 23rd. That was certainly a contribution to the warmest February on record with 54 degrees. I'll leave that up there for a second so you can take a look at it. All right, moving on to Greensboro. I'll leave this slide up here and I won't read the entire slide to you, but I will point out again that we had the warmest daily February temperature on record. It was 81 degrees on February 23rd, 2023, and that helped contribute to the second warmest February on record this year. And last but not least, taking a look over the last 5 years at Fayetteville, and once again, February 23rd of this year was the warmest daily temperature that we have on record in Fayetteville. It was 85 degrees, and that helped contribute to the warmest February on record. Oh, sorry, not the warmest February on record. That was 2018. 2023 was the fourth warmest February on record. And I'll give you a few seconds to take a look over these numbers. Now, I said that we haven't had too many cold spells recently. I threw a lot on this graphic, so let me walk you through it. In Greensboro, if you take a look at the average daily highs, in the summertime, they might be in the 80s, approaching 90 degrees. The coldest average daily high in Greensboro is 49 degrees, and that occurs in the middle of January. What is the actual coldest high temperature that we experience each year? If you take the coldest daily high temperature over the last 30 years, the coldest day that we end up having on average is 28 in Greensboro. If we look over that 30-year period, what is the average low on a day on the coldest day in the middle of January? It would be a high of 49 and a low of 30 degrees. But how cold did we actually end up dipping each year? From 1991 to 2020, the coldest low temperature that we experienced over those 30 years ended up averaging to 11 degrees. So last December 24th was a very cold stretch compared to what we have had in several years, where you can end up seeing that we dropped all the way to 5 degrees in Greensboro that day. And I can't remember between Greensboro, Raleigh, and Fayetteville which city was which, but I know that for one of those locations, that was the coldest temperature that had been experienced in 5 years. For one of those sites, that was the coldest that they had been in 10 years. And for the other site, that was the coldest that they had been in 20 years. So in that sense, we did have a very cold stretch, at least that one particular day, December 24th of last year. Moving on from the temperatures, next we'll end up going over a snow climatology for the area. So this graphic was put together by the North Carolina State Climate Office. This is looking at the annual snowfall, again, over our latest 30-year climatology period, 1991 to 2020. It's a broad scale climatology. It is not trying to cover every little portion of every county. I'm sure that if we were to go into the mountains, you would be able to pick out particular mountain peaks, Mount Mitchell, for example. You would be able to find particular places that have peaks and valleys when it comes to those snowfall totals, but this is just a broad sense of what ends up going on over the state. This is another way of looking at a snow climatology. This is courtesy of Eric Webb. You can find him at Weber Weather on Twitter. He used several different sources to end up generating this graphic. It's from 1948 to 2021. And so this is taking a look at the chance of having a winter storm somewhere in East Central North Carolina. So you can end up seeing that to have a minor event, which he classified as at least 1 inch of snow or a trace, that's any accumulation of freezing rain, that climatology peaks somewhere in the middle to end of January. But if you end up looking at major snowfalls, extreme snowfalls, or the historic snowfalls, all of those occur a little bit later. Those all end up peaking somewhere in the middle of February for the most part. And you can see that it's not impossible for us to end up having some amount of snow after April 1st. So what is the ratio of snow to liquid? Everybody talks about a rule of thumb that if you take 10 inches of snow and melt that down, that you'll be left with 1 inch of water. That is the measured the most often locally, looking at that bar chart in the bottom with the red. But many times that ratio is not true. So you can end up seeing that 80 something times that the ratio was 6 to 1 or 8 to 1. And that graphic, that kind of odd shape, that's our forecast area between the aqua and the dark blue and the light blue. And what that is doing is the research was taking a look at how the average ratio of snow to liquid varies over area. So the snow is typically a little bit wetter, heavier, more dense in the southwestern portion compared to the northeastern portion, where you can end up seeing the blue and just a little touch of kind of some darker red in our extreme northeastern area. Now, this map has older data. I have not seen it refreshed. This is showing a good portion of the United States, the snow to liquid ratio from 1971 to 2000, not 1991 to 2020. But again, this generally ends up showing you that the dark green area covering a lot of North Carolina is an average of 10 to 1 for that ratio of snow to liquid. However, if you go into the Rocky Mountains, you end up having higher ratios. You might have 14, 15, 16 inches of snow per inch of rain. And you can also end up seeing around the Great Lakes, lake effect snow. You can end up having higher ratios as well. The snow might end up being a little bit fluffier. There was one time when I was working in Upper Michigan that we ended up measuring a ½ inch of snowfall, but the liquid gauge said that we had less than 1/100th of an inch of rain. So that was more than a 50 to 1 ratio. When I had that ½ inch of snow on the windshield of my car, I was literally able to and just blow my breath out onto the windshield, and it ended up scattering all the snowflakes. That's how little mass there was, how little water there was in that snowfall. So taking a look at the snowfall statistics for Raleigh and Greensboro, again, as I said earlier, we do not have an official climatology for Fayetteville. You can end up seeing that in every month other than November, Greensboro does end up averaging a little bit more snow than Raleigh. There's no one month where it really ends up sticking out, but you can see that over all of those months that there's some additional snow that ends up occurring. Here's some graphics that were put together by, again, the North Carolina State Climate Office. These have not been updated to include the winter of 2022-2023. So this was valid after 2021-2022 season. The color scale at the bottom left shows you how recently these different events end up occurring. And so the State Climate Office ended up determining that most of the state ended up having a 1-inch snowfall event during that winter. However, if you go to the extreme southern part of the state, you can see that you would have to go all the way back to January 11th, 2011 to end up finding where those areas ended up having 1 inch of snowfall. We have a lot more variation here for the last 6-inch snow event. Again, across Wake County, depending on where you are in the county, that might have occurred in 2014, or it might have occurred in 2018, or it might have occurred in 2010. And again, there's a little stretch across the eastern part and the southern part where you have to go all the way back to 1989 to end up finding a snowstorm event where there was at least 6 inches. And then finally, if we end up looking for the last 12-inch snow event, For Wake County, you have to go back either to the January 2000 snowstorm or the January 2002 snowstorm. And again, some portions of the state, you have to go back into the 50s or the 70s. And there's a small area that might have been all the way back to 1927. Certainly, as you end up going out to the mountains, much more recent, January 22. And again, I have not seen the State Climate Office issue any new graphics so far because they normally release them in December. I have not seen them release any of these graphics yet that include this most recent winter. Taking a look at a winter precipitation climatology and the number of events per year of sleet and freezing rain. You can end up seeing that in Wake County, we average somewhere between 4 to 6 events of freezing rain and sleet per year. You would end up having to go up towards the Triad, up in Winston-Salem and Greensboro and points north to end up finding more events with freezing rain and sleet. A lot of time that's caused by cold air damming, where we end up having cold air at the surface and then a layer of warmer air above that and the cold layer. And so again, going back to those graphics, you need to have cold air, then warm air, then cold air, and that happens the most frequently in the Triad. If you take a look at the average number of events per year of snow and sleet accumulation, it's no surprise that as you end up going out to the mountains, that's where you end up having the most snow. Again, going out by the coast, you would end up averaging 1 event or less each year of snow and sleet. Taking a look at the snowfall for Raleigh, there's a lot going on this plot. So this is showing all the way back to 1887 through the 2022-23 year. And that blue trace shows you how much snow ended up occurring each winter. The red line is the running 30-year average. So you can end up seeing that if we were taking a look at snowfall from 1890 to 1920, that the 30-year average was closer to 10 inches, and slowly over time, it has ended up going farther down. The green is showing a 10-year running snow average. So again, you can see peaks and valleys there going back and forth. In the upper right are the 5 snowiest years in Raleigh history. Again, we already talked about the 31.6. Many more people are likely to recall the 1999 and 2000 winter with 25.8 inches of snow. The reason I wanted to show this very busy graphic is the fact that you can end up seeing that there aren't that many years near the yellow line, and that's the 1991 to 2020 climatology. There have only been 16 years going back to 1887 where we were within 2 inches of snow of that climatology line, somewhere between 3.2 and 7.2 years. So we really shouldn't talk about normal snowfall. It really is an average in this case. You'll end up having a couple of years with a very low amount of snow. You can end up having 1 year with a high amount of snow, and it all averages out. So when we end up talking about average temperatures being 70 degrees for high temperature, you can average everything out, and you probably do have a good number of 70-degree days in there. When it comes to snowfall, though, we don't have that many years that are right around 5 inches of snow. So it really is an average in this case. I also wanted to take another look at the amount of snowfall RDU. If you were to drop the tenths of inches and just use the integer, the number in the ones digit, so if you have that 5.2 inches of snow on this map, on this graph, it would show up as 5 inches. If you were to take all of those years of snowfall back here and just say, okay, anywhere between 0 and 0.9, I'm going to count that as 0. Kind of you drop the remainder. Having less than 1 inch, that is actually the most frequent interval, 1 inch interval of snow that we have, with the next most common being somewhere between 2 and 3 inches. And you can see how many times we've ended up having all of those different amounts of snow. I only showed up to 12 inches of snow. There were 23 seasons that had at least 13 inches of snow. Now going to Greensboro. Again, the highest snowfall that was measured there was in the 1926-27 winter with 32.5 inches of snow. You have to go all the way back to 1966, more than 50 years ago, to find a top 5 snowfall for them. Again, the period of record is shorter here. It goes back to 1903 instead of 1887. Again, you can end up seeing that, taking a look at that red line, that starting off the period of record, it was below 5 inches, and then it's gone up, and for a little while it was actually up over 10 inches, and it has come back down towards 7 inches. Again, if Raleigh had about 15 years within 2 inches of the climatological normal, Greensboro doesn't have that much more. It's 21 years, over 120 years of record keeping. So again, you can see how up and down that blue line is. You can really see that there are some years with a good amount of snow, but you have plenty of years with only a little bit of snow. So when we end up talking that Greensboro has about 7 inches of snow each year, it really is an average. There isn't really a normal year where we're having 7 inches of snow. And again, if the average snowfall is 7.1 inches, the most frequent amount that ends up occurring is less than an inch. Interestingly enough, we spike all the way to somewhere between 8 to 9 inches to be the next interval where we end up having that amount of snow. And there were 18 seasons with more than 16 inches of snow. All right, moving on to a set of products, and then we'll go on to some product definitions from there. We have 3 levels of notification: a hazardous weather outlook, a watch, and an advisory/warning. And I'll tell you why I lumped those together in a minute. The hazardous weather outlook is something that generally discusses storms or events several days in advance to alert the public for the potential of some sort of hazardous weather, and allows for early planning and preparations. This could be for winter weather, for severe weather, for extreme heat, for extreme cold, for a wide range of weather. And this is issued with about 30% confidence that we will have warning criteria at any time during our 7-day forecast period. Watches are issued for a heightened potential of warning criteria event. And when we're looking at the winter time, those warnings would be winter storm warnings, blizzard warnings, or wind chill warnings. And these are issued when we have about 50% confidence that we will reach warning criteria. And finally, a warning is issued when we have a high probability of warning criteria, again, a winter storm, a blizzard, or a wind chill warning, or the warning criteria is already occurring. And this is issued with about 80% confidence of the warning criteria. Now, I lumped warning and advisory together earlier as levels. An advisory is also issued when we have about 80% confidence of an event happening. But in this case, it's going to be something that we think is a nuisance, but is not necessarily life-threatening. And a little bit later on, we'll end up going over exactly what those criteria are for warnings and advisories. But warnings and advisories are both issued with about 80% probability. Do not think of a watch going to an advisory as a downgrade. Although warning criteria is higher than advisory criteria, the issuance of an advisory still means that we have high confidence that there's going to be important impacts. The watch is a 50% probability of something happening. The advisory is an 80% probability of something happening. And then this is another good graphical way to visualize the difference between a watch and a warning. Marshall Shepard ended up getting this idea from Weather Brad Panovich. He is the chief meteorologist at the NBC station in Charlotte, showing that a watch is when we have the ingredients for something to occur. So we have the butter and the sugar and the flour and the eggs. We have all the ingredients for a cupcake, but we don't actually have a cupcake at this point. We issue the warning when it's about to happen or it has occurred. Now we have a cupcake. It's here, it's there, it's going to happen. That's similar to us seeing that we have the ingredients coming together to have winter storm criteria. So if the ingredients are coming together, we would issue a winter storm watch. If we actually have that happening, that's when we end up issuing the winter storm warning. So again, just putting all of this onto a single slide. The watch is when significant winter weather is possible. The winter storm warning is when severe winter weather is occurring or is already imminent. It is already occurring or is imminent. And a winter weather advisory is when you can expect some travel difficulties that won't meet warning criteria, but there will still end up being travel problems in all likelihood. Moving on from that, let's get into some product definitions. Locally, for our forecast area, we will issue a winter storm warning if snow is the only hazard that we are concerned about. If we are expecting to have 3 inches of snow in 12 hours or 4 inches of snow in 24 hours. This criteria changes throughout the country because different areas receive different amounts of snow. If you end up going down into Florida, it might be 1 inch of snow in 12 hours would end up being a huge problem. If you were to end up going up by the Great Lakes, you might need to have 4 inches of snow in 12 hours or 5 inches of snow in 12 hours because they have snow more frequently and they are more used to it. So that criteria is not the same throughout the country. Locally in North Carolina, a winter storm warning for ice, specifically for freezing rain, is when we end up expecting to have at least 1/4 of an inch of snow for the storm total itself. And a winter storm watch could be for snow or ice, where we believe there's the 50% potential for winter storm warning criteria in the near future for that 3 inches of snow in 12 hours, 4 inches of snow in 24 hours, or the 1/4 of an inch of storm total ice. A winter weather advisory issued for snow is when we expect to have at least 1 inch of snow in 12 hours or a mix of accumulating snow and ice. If freezing rain is the only precipitation type that we're expecting, any accumulation of ice will prompt us to issue a winter weather advisory, because any amount of ice can end up causing huge travel issues. And so we always want to make sure that people are aware of that. Taking a look at the climatology, this is going back, this is in a 30-year period, and these are slightly different time periods by a matter of weeks. But this is taking a look between December of 2005 and February of 2022 for our forecast area. The last winter weather advisory that we issued was on February 7th, 2022, and the last winter storm warning we issued was January 21st, 2022. So that's the reason those dates are slightly different. But this is taking a look across our forecast area and seeing over those years how often we typically issue an advisory and how often we issue a warning. So you can see down in Sampson County, we average about 2.83 advisories per year. But then as we end up going up by Forsyth and Guilford counties, that's where we end up having our most advisories. And they average just over 5 winter weather advisories per year. As we end up taking a look in the right-hand side, taking a look at the winter storm warnings, again, Sampson County averages 2/3 of a warning each year. Yes, we can't issue 2/3 of a warning, I understand that. But you can end up seeing that if we look around Wake County and Raleigh, we issue about 1 warning per year. And you can see Person County, up where Roxborough is, they end up having the highest average of 1.61 warnings per year. Okay, so these are our 31 counties that we forecast for. How does this compare to the rest of the state? These numbers are going to be a little bit different because this ends up including through 2023. So that's why the numbers, if you saw on this left graphic, it's 4.22 for Wake County where Raleigh is, it's only 4 here because these timescales are not exactly the same between the 2 slides. But you can end up seeing that there are portions of the mountains that end up averaging 12 advisories a year and about 5 warnings per year. Meanwhile, our neighbors out by the coast, You can end up seeing numbers as low as 0.11 advisories. So over 18 years, that means they probably had 2 advisories over that entire time span. And there were even a couple of counties in North Carolina that did not end up having a single winter storm warning in this 18-year period. Now taking a look at some of our other winter weather criteria, we will issue a wind chill warning when the wind chill values are expected to be 15 degrees below zero and colder. We will issue a wind chill advisory for any wind chill values that are going to be between 0 degrees and minus 14 degrees. Then taking a look at wind products, we will issue a high wind warning if we expect sustained winds of at least 40 miles an hour for at least a full hour, or any gust at least 58 miles an hour. 58 miles an hour sounds like kind of a weird number. 58 miles an hour is equal to 50 knots, which is 50 nautical miles per hour. So 58 seems like an odd number. It is a round number using a different unit of measurement. 58 miles an hour is also the criteria for severe thunderstorm warning. So you may have heard of that number from that as well. Wind advisories are when we expect sustained winds of 30 to 39 miles an hour for at least 1 hour, or any gust of at least 45 miles an hour. And I will say that for a wind advisory and a high wind warning, it is very rare that we end up issuing these products because we have sustained winds for at least an hour. Almost every single time we issue one of these products, it's going to be because we're expecting those gust values. And again, just putting all of these wind chill products onto a single slide so you can take a look at this. So what is some of the science of wind chill? If there is no wind, your body averages 98.6 degrees, and so your body will radiate some heat outward, but it kind of creates a layer of warmth between your body and the cold surroundings. When it's windy, that heat that is radiated from your body gets shoved away by the wind, and it doesn't serve as that insulating layer. And so you'll end up feeling the colder air that much more. Blizzard warnings. There are 3 criteria to issue a blizzard warning: frequent gusts of 35 miles an hour or greater, snow, whether it is blowing or falling, reducing visibility to 1/4 mile or less, and this has to last for at least 3 hours. It is very rare to end up getting visibility to remain less than 1/4 mile for 3 hours or more. And so blizzard warnings are not dependent on snowfall accumulation. I'm kind of cheating by having this picture where there's a car stuck under snowdrift. Because blizzard warnings are not dependent on the snowfall accumulation, you could have 2 inches of snow, but if you had the gusty winds and the reduced visibility for 3 hours, that could prompt a blizzard warning. The Raleigh office has never issued a blizzard warning. We haven't had that criteria here. And finally, we'll end up getting into a bit of a miscellaneous category, kind of covering a whole bunch of things that didn't fit into any one of those nice categories that we had earlier. What are some of the major types of systems that we would have for wintry precipitation in the Raleigh forecast area? We have Alberta clippers, nor'easters, and cold air damming. So now Alberta clipper is a system that forms over the province of Alberta. And since the system develops over land, there's normally not as much moisture with it. So it'll probably end up resulting in a lighter snowfall, even if the coverage is widespread. Again, as the name suggests, they get their start over Canada and move across the northern states. When it says a narrow band of dry but significant snow, that's talking about those higher snow ratios as opposed to the wet snow, which is the lower ratio, which is the wet and heavy snow. Taking a look at nor'easters, they can be named for 2 reasons. One is that the storm motion is heading towards the northeast. It's also for the fact that you experience northeasterly winds on the leading edge of the storm. And nor'easters typically form and move up along the east coast, Many of them passed east of our forecast area, but not all of them. We certainly ended up getting a good amount of snow here, over a foot, with the nor'easter that ended up moving up the East Coast in March of 1993, ended up bringing lots of snowfall from New York down into North Carolina, and there was even severe weather and tornadoes in Florida with this particular storm. Not many types of storms have the potential to give 100 million people 1 to 2 feet of snow in a day. And again, it's normally that heavily populated region between DC, Philadelphia, New York, and Boston that would end up having the biggest impact from a nor'easter. Finally, we'll also end up talking about cold air damming. Again, we were talking earlier about how you end up having sleet or freezing rain because you have cold air much higher in the atmosphere. You have a layer of warm air, and then you have cold air towards the surface. So what can end up happening here in North Carolina in particular is if we have high pressure bringing clockwise motion, and so you would end up bringing air from New York down across New Jersey and the Delmarva Peninsula into North Carolina, that's going to be your cold air that you end up having at the surface. If you end up having air moving from east to west, that air can end up rising up and over that cold air because warm air rises. So as that air is pushed west, it'll rise up and over the mountains. And so that's how you can end up having your cold air at the highest levels of the atmosphere, then a layer of warm air, and then colder air at the surface. The most difficult part of the forecast with this is figuring out how thick that warm air and that cold air is going to be. And so again, in that upper right-hand image, it's kind of saying, okay, you know, what is the depth of the cold air? How much warm air do we have? And then in that bottom graphic, it's showing that depending on where you are, that will end up determining what type of precipitation that you end up having. And so one of the most difficult things for us to forecast is the thickness of the cold air and the thickness of the warm air, and exactly where those layers are going to line up. And that is the reason that it's so difficult for us to end up forecasting precipitation type here in North Carolina, because a very small difference in that snow and mix line or that rain and mix line, if those lines move 10 or 20 miles to the west or the east, that can end up resulting in huge changes in our forecast and what precipitation type will occur. So another thing that we end up hearing about frequently, if you have lightning in the winter, does that mean we're going to end up having snow? I'm sure a bunch of you are thinking about this after the weather that we ended up having back on Sunday and the thunderstorms that we ended up having. So this slide is showing some research that was done by Corey Davis of the State Climate Office. I've included the link there. He ended up going through that. He did this probably, well, it says this is the post that he did 10 years ago from December of 2013. So he ended up going back from the late 1940s through 2012, and he took all lightning reports at Asheville, Charlotte, Greensboro, Raleigh, Wilmington, and Hatters. So a wide range of areas across the state. And he found that during that time period, there had been 642 days where thunderstorms occurred. And then a lot of times people end up saying that, well, if you end up having a thunderstorm in the wintertime, you'll end up having snow within a week or so. He ended up finding that there were 85 cases where snow was observed 7 to 10 days later. So a lot of times, kind of that folklore ends up saying it'll be 7 days. He even went out as far as 10 days. And so when it comes to that, we only ended up having snow 13% of the time afterwards. So a lot of people end up making it sound like it's a lot more common that we end up having snow if we end up having a thunderstorm. But really what Corey's research ended up showing was that it only ends up occurring about 1 in 7 times. All right, and so for a little bit of a talk, a lot of you have probably heard about El Niño and what that will end up doing to our forecast and what that will end up meaning seasonally. And so to talk about that, we have one of our climate experts in the office, Brandon Locklear, here to end up telling you more about that.
All right, hi, good evening, everyone. And no, I'm not a climate expert, but I really have a passion for climate. I try to learn as much as I can. And I do a lot of the climate program work here at the Weather Service in Raleigh. So we're going to go over the winter outlook. And I think most people have seen this. It gets a lot more attention, and rightfully so, than what it used to. What we're going to do is we're basically going to go into, what's the driving factors of this forecast. And what you see here on the graphic, we'll start on the left-hand side with the temperature, the seasonal outlook is, you see a lot of oranges and reds across the northern portions of the United States. And then down across the south, you see a bunch of white, or what we call equal chances. People's like, well, they just don't know they don't know what's going to happen. And that's not the case. And I'm going to show you why. Because we actually have some help this year in trying to make this prediction. And when you have these climate forecasters that are trying to make these seasonal outlooks, you're talking about 3, 4, 5, 6 months out. There's a couple of climate teleconnection patterns that they love to see form, and we have that this winter, and that's what provides us some confidence. And that's why you see on the right hand side a very dark green showing above normal chances for rainfall for the next 3 months. And we might already be kind of seeing that starting to develop. And so we're going to discuss some of the factors that's driving that. And I love this cartoon here. So after having 3 consecutive years of La Nina, and we're going to talk about what La Nina is, we finally have El Nino. And we're already on the threshold of having a very strong El Nino. They define El Nino by temperatures averaging, or temperature anomalies averaging 1.5 degrees Celsius above normal in the tropical Pacific. And you're going to see this here in this graphic on the right hand side. And we are on the cusp of that. And you need to do it for like 3 consecutive 3 series months. So it needs to be like a 6-month to 9-month period. And so real quick, let's talk about what it's going to be a real quick refresher. Let's talk about what El Nino is and what ENSO is. But the El Nino, it's the Southern Oscillation, abbreviated ENSO. It is the most influential natural climate pattern on Earth, and we love to see that because that gives us some confidence, because temperature and precip patterns emerge in the cool seasons in the winter. And El Nino, which is what we currently have, and we're on the cusp of having a strong El Nino. That is where you have, and you look in the lower right here, that's where you have above normal temperature anomalies over the central and eastern Pacific, okay? And the opposite of that is La Nina, and that's where you have the cooler than normal sea surface temperatures. And on average, you kind of oscillate back and forth between this La Nina and El Nino every 2 to 7 years. And every La Nina or El Nino is a little different. So even though we had that, what we call that triple dip La Nina for 3 consecutive years, ending in 2022 and 2023, everyone's different. Sometimes it's about where it's at in its maturity. As you get into the winter, it's about the depth of those temperature anomalies in the ocean. So everyone's a little different. You just can't compare, since we've got La Nina this year, we're going to expect the very same, but there are some patterns that emerge. And what happens when you have that irregular gradient and oscillation between warm and cold air, that affects, warm and cold ocean temperatures, that affects the atmosphere. It affects the jet stream. It's going to shift it. It's going to weaken it. It's going to make it stronger. And that's how we see different patterns emerge away from the tropics. in the Pacific Ocean. We see it really globally, but there is a very strong impact in the United States during the winter months. Okay, and then if anybody that's in the climate, you know, this is a very famous graphic here. Well, basically, when we were in El Nino, you see the shift of our jet stream. That's going to be this tropical jet stream. It's going to shift a little further south, and it's going to be over the southern United States. Okay, and if you can think of again about what that precipitation outlook looked like, you know, where the wet areas were, it was in close proximity to that southern stream jet. Okay. So now the next series of images I'm going to show you are what we call ENSO composites. And so what they've done is they go back and they look at all the La Nina, and they look, which is the cool episodes, look at the El Nino, the warm episodes, and they take all those years and they group them together and they try to see these patterns emerge. We also have a third category, and that's what we call neutral. Okay, so when you look at this graphic, you can see there is and what this is a correlation or a relationship to ENSO and precipitation. And again, there's those deep greens. You remember on the outlook, we saw that very high percentage of above normal rainfall. Well, that's what happens. And when you look at the green, that means you have more precipitation in El Nino events or El Nino winters, because this is for December through February. And then if you see the purple, it's the opposite. You actually see more precip in La Nina years. And the darker the colors, the stronger relationship. So you can see across all the southeastern United States, including North Carolina, we have that strong relationship. Now, what we've done here in this graphic is we've looked at the last time we've had strong El Nino conditions, because again, I told you we're on the cusp, and all the climate models are showing that we're going to have a strong El Nino through at least the spring. And what we've done, there's eight seasons, and you can see those seasons in the bottom of this graphic, and you can see that out of 8 winters where we had a strong El Nino, we observed above normal rainfall. Okay, I mean that's batting 1,000, right? And then you see some dark green, so it is a very, very high likelihood of seeing above normal rain. Okay, and it matters. The strength matters. Okay, so when you look at on the left-hand side, a strong El Nino versus a weak, these are the precipitation departures. So you can say how much above normal or how much below normal. Okay, so you can see when we have a strong El Nino, you know, we could see some pretty significant surpluses in rainfall, and that's very important as we head into the winter. Most of North Carolina, especially central North Carolina, was starting to see a growing and intensifying drought. And then as you get into a weaker El Nino, you don't see as much positive rainfall amounts, a surplus. So now we're going to switch to temperature. And you can see we also have a strong relationship when it comes to El Nino and ENSO and La Nina, the whole system. We have a strong correlation across the South and the Southeast with temperatures as well. Maybe not as strong as precipitation, but it's definitely a strong relationship. Okay. And then again, when you look at the 8 seasons where we had the strong El Nino, out of the 8, you can see on average 5 of those winters ended up being above normal. Okay. Now, if you remember back at our temperature outlook, it had above normal just across our north, and it was near normal. So what's going on there? And you can kind of see that depicted here in this graphic down across South Carolina, but they have it well across most of North Carolina. So let's investigate that a little further. And so what we're looking at is on the left-hand side, we're looking at strong El Nino events versus on the right-hand side, weak. And your 2 top graphics are your maximum temperature anomalies, and the bottom 2 are your minimum temperature anomalies. And again, strength matters. Okay, the stronger the El Nino, the better the pattern is going to emerge. But the really interesting thing here is that, now remember, what does those sea temperatures in the tropics do? It shifts that jet stream. The jet stream's where all of our precip events occur. So we have that jet stream extending across our region. So we're going to have more clouds. We're going to have more precipitation. So what that means in the top left, we're going to have cooler days. And then at nighttime, we're going to actually have warmer nights. So what can happen is that those can tend to offset each other. And if you look, the minimum temperature anomaly is actually stronger than the maximum temperature anomaly. So when you look and you talk about above normal, it's those above normal nights that ends up making our winter average temperature above normal. So they can tend to basically offset and balance one another. And when you look at those anomalies at a weak El Nino, they're much weaker. Now we get to snowfall, and notice what's happening to our colors, right? They're not as dark. And so that means that relationship for when we look at ENSO, El Nino, there's not a strong relationship there. It's actually pretty weak. Okay. So the purple, again, it means more snow in La Nina, which is very interesting that we actually have that extending across South Carolina and into North Carolina. And then the opposite, where green is actually a little bit more through El Nino. But again, notice how the colors are a lot lighter, the relationship's a lot weaker. In fact, when you do some significant, like some statistical analysis on this, it shows that there's not a significant relationship in this. Okay, so we have to be very careful when saying that, well, we got El Nino, then this is going to be our chance to see a very snowy winter. This is looking at our eight strong El Nino years again. And, you can see here as we get into like the northern portions, out of 8 strong El Ninos, we've only seen 3 of those that had above normal snowfall. And there's actually a little bit more of a pattern across eastern North Carolina where, you're looking at 5 out of the 8. But you got to be real careful. Again, there's only 8 events, and you do a statistical analysis, it shows, well, it's not that significant. What I did here is I took the 8 years that we made these composites for this image here. I broke them out individually, and I just wanted to show you how things can vary. So when you look from 1958 to 2016, you can see there's some winters where where basically it was a drought. And then you can see a couple of really snowy winters, the one more recently for 2010, where it was actually a very, very snowy winter. Okay. And the big thing you got to remember here is there's other climate anomalies and patterns that emerge in the winter that can actually, for a short period of time, become more of the dominant weather or climate producer. And those are the things that are difficult to forecast really beyond 2 to 3 weeks, maybe month, with any kind of confidence. And that's what we're missing in today's age of trying to make long-term predictions. Real quick, I wanted to show this. I said you got to be real careful, but basically what you're seeing here, we got 2 snow reporting climate sites, and Tom has mentioned these. One's in Greensboro at the Piedmont Tri Airport, the other one's at the Raleigh-Durham Airport. And so when you look at the actual observed snowfall at these 2 sites, basically from 1950 to 2022, you can see there is a slight increase in your average snowfall during El Nino winters versus neutral or La Nina. And this would take into account all El Nino events, weak, moderate, and strong. But you can definitely tell there's an upward little, a little increase there. So again, that's one real quick. The takeaways is that ENSO, that's when the long-term climate models were showing that we were going to have an El Nino winter, and it was showing the potential for it to be really strong. The climate forecasters and experts, they love this. I mean, this is something that we know it produces these patterns. And so that's why we can have high confidence that we are definitely going to see, more than likely see a wet winter. And I think we're seeing that starting to emerge here. And the temperatures, that there's also a pretty good correlation with that across our area. Snowfall, we got to be careful about. Is, you know, the relationship's not nearly as strong. And then what you have to keep in mind that if at the end of the winter, you know, if it turns out that, hey, you know, what happened here, the temperature forecast ended up being, we ended up being well below normal. And that's when we need to look at some of the other climate anomalies I kind of referenced earlier. The polar vortex, the way we measure the polar vortex is called the Arctic Oscillation Index. We can see certain winters where that can a negative, what we call a negative AO, which means the Arctic's open for cold air into the southern part of the United States. It can dominate, and it can dominate for like basically weeks at a time. And if we can have that happen, you know, and we have that active southern stream jet, then that can be the ingredients for us to have, you know, potential of a winter storm and maybe being well below normal. And that is it for me. I think Tom's going to make this graphic available. Here real quick is just the years that we observed El Nino for your reference. Thank you.
Appreciate it, Brandon. Thanks. You're going to stick around. We'll, I just have a couple more slides to go with my part of the presentation, and then we will open things back up for questions. So let's see. Let me get my report back up here. All right. So assuming we do end up having snowfall this year, and that we aren't, you know, we won't have 5.2 or 7.1 inches. We'll have more than that, or not a lot. So what are 6 basic steps for properly measuring snow? Supplies that you want to have a ruler or a yardstick. It's good to have a white board, just like a white wooden board. The reason you want to have a white surface is that it will end up reflecting any sort of light and not absorb the heat. You don't want to melt your snow on the surface that you're using. So you want to find an open area away from tall objects, but sheltered from the wind. You don't want the wind to drift onto your snowboard. Set this up before your snow begins, and then if you have a flag or something, that can end up helping you mark where your board is so that you can find it later on. You want to record your totals to the nearest 1/10 of an inch. And you want to measure once daily at the same time. Then when you're done, place the board back on top of the snow. We typically like to end up getting our snowfall measurements. A lot of the places that we end up getting the data from, they'll end up letting us know at 7 or 8 a.m. in the morning. Also, if the snow stops and the sun comes out and everything's starting to warm up, you want to measure as soon as you can when the snow stops to make sure that you don't end up getting a lower number because the snow ended up melting. And then make sure you send your report to us. Go on weather.gov, go on Facebook, Twitter, all different ways to give us your report. There are a couple of different ways that you can end up measuring ice. If you end up measuring ice, please make sure you tell us if your measurement is flat ice or radial ice. And so again, I won't read the slide to you, but if it's flat ice that you're measuring, you want to find a flat surface that has been undisturbed. Use a ruler to end up measuring that. Or if you're looking at radial ice, you'd want to end up looking at what the overall thickness is and then divide that by half to end up getting what the average measurement is on either side of the branch. Finally, what is the type of stuff that we want you to report? We need your snowfall reports, especially if the snow manages to pile as high as the high intensity power lines. Anytime that you report weather to us, please make sure to give us your location, including your county, because we do have some town names that are duplicates between counties, and the time of your observation. For snowfall, I was saying that you would end up wanting to report once a day. You can also end up reporting every 6 hours if you'd like. We do not want hourly snowfall measurements. Those are, it's apples and oranges compared to the other types of reports that we're getting. So we'd want every 6 hours or every 24 hours, and then what your total snowfall is. For freezing, drizzle, or rain, we want to know about any occurrence, because again, if there's any freezing, drizzle, or rain, that would prompt us to issue a winter weather advisory. We would want to know again if you end up reaching at least 1/4 of an inch of ice accumulation, because that's reached our warning criteria. And then we'd also want to know whatever your total ice accumulation is overall. Certainly, if you end up having any thunder or lightning with the snow, sleet, or freezing rain, we'd want to hear about that. That isn't automatically going to prompt an advisory or a warning or anything like that, but it lets us know that the atmosphere is very dynamic, and that certainly means that we could end up having some heavy rates of winter precipitation going on. And we'd also like to hear about any wind speeds that you have that are at least 40 miles an hour if you've measured them. Everybody overestimates the wind speeds that actually end up occurring. So we really only need these wind speed reports from you if the wind speed has been measured at least 40 miles an hour. So how can you submit a report? You can send us an email at nws.raleigh@noaa.gov. You can visit us on Facebook or Twitter using NWS Raleigh as our handle. We have a Skywarn number. It's 919-326-1041. This allows you to speak to a forecaster 24 hours a day, 7 days a week. However, please do not give this phone number out to other people. This is a phone number that we specifically give to people who have ended up going through our spotter training. So we know that you have additional training. If you want to end up giving another number to your friends and family, give them 1042. That's 919-326-1042 is the number that you can feel free to give out to anybody. But you who have done the training, you can feel free to call us on 1041. And remember, even though it's rare, we can still have summer severe weather during the winter season as well. Just look at 2 days ago in Gardner where we ended up having the EF1 tornado. So all rules for those types of reports also apply. Did you know that the Weather Service uses CocoRa's reports for river forecasts and flood warnings? I took this from my previous office in Pittsburgh. CocoRa's is the community for collaborative rain, hail, and snow reports. And so they are not directly affiliated with the National Weather Service. However, we certainly end up using the data that they end up collecting. We end up submitting our data to the CocoRa's website as well. So you can learn more about them at cocoras.org. There's also the MPING project, Meteorological Phenomenon Identification Near the Ground, and you can let us know what precipitation type is happening at your location. There's a free app that you can get through iTunes or Google Play. You can end up, if you look in the bottom left-hand portion of this graphic, it'll end up showing you all these different types of weather that you can end up reporting to us. You can test it out and then look on the map to see where you are and see that there was what was going on, that you were just testing it out, or you can report that there's nothing. You can report fog, drizzle, freezing rain, wet snow, all different types of weather phenomenon you can end up putting on here, and then you can end up viewing it as well. And with that, that brings us to the end of our presentation.